So let's have a look at page 670 there. Look at kinetics. Now, kinetics looks at not only the motion, but what causes the motion. Okay. So let's have a look at that. We're going to look at using F equals ma, and now we're going to add something new because we're looking at entire objects that can rotate as well as translate. So we're also going to look at m equals I alpha and some variations on that. Okay. So let's say we've got an object that's moving through space. What we're going to do now is identify the center of gravity of the object, and that will serve as our reference point. So sum of F equals ma, we subscript the a now with a g, meaning center of gravity. So if you have an object moving in free plane motion like this axe here, and what's going to move in that smooth kind of trajectory would be the center of gravity. So our F equals ma will apply to that. And in some cases, when we're analyzing this stuff, that will serve as our reference point. Okay. We're going to introduce an analogous equation to this too. If we take the F and turn it into a moment about the center of gravity, what happens is A turns into alpha, the linear A acceleration turns into a rotational alpha there. And the mass turns into a moment of inertia. That's why we were looking at moment of inertia. So sum of mg, the sum of moments caused by these forces about the center of gravity, which serves again as our reference point, is Ig alpha. Now the last thing that we'll develop here will be an equation if we don't take moments about the center of gravity, if we take them about some other point A here. Okay, so if we go sum of MA, we're still going to have an IG alpha term, but now we've kind of offset our moment away from the center of gravity. So we'll have to consider the inertial moments that could be caused by accelerations of the center of gravity. These are called inertial moments. And what they are is the mass times the acceleration of the center of gravity in the x direction, which is an inertial force, multiplied by a y bar distance from A to the center of gravity, because that causes what we call an inertial moment. Similarly, we'll look at the mass times AGY, because again, our center of gravity is our reference point, and multiply that by an offset x bar distance from A to that point, that center of gravity, okay? So that's an inertial moment equation that we'll use sometimes to analyze objects. And this accounts for the fact if you're taking a moment about a point other than the center of gravity, you have to account for the MA effects on that center of gravity plus an offset distance to create an inertial moment. So the x acceleration of the center of gravity has a y bar distance that it's multiplied by, that creates a moment, okay? And the the y acceleration of the center of gravity has an x bar moment arm, okay? So we're going to look at three versions of this. First, we're going to look at just translation, objects that move in a straight line or some sort of parabolic line. Something like that, a motorcycle moving to the right. We're going to look at whether or not something might tip too. Okay, as shown there. Okay, we're also going to look at fixed axis rotation, an object just rotating about an axis, and then we'll look at free plane motion. All right. So let's have a look here at an example of applying these equations up here, the F equals ma and that inertial moment equation, to a everyday situation here. If you're at the checkout line there, you ever notice those conveyor belts they got? I often wonder, will this water bottle tip if I put it on the conveyor belt? I'm sure y'all being engineers think about that too.
That's an engineer thing to think about.
Yeah, right. So I'm sure they've got their engineers working on this. I don't doubt that. Okay, so here's how they might analyze that. Okay, so these water bottles are kind of top heavy, aren't they? Okay, So let's have a look here. Let's do a few things. Let's get the dimensions of the water bottle. So we'll use a ruler and we'll measure those. And then we're going to calculate where the center of gravity of the water bottle is. It's probably going to be a little high centered there because of that heavy lid. Now, of course, we could do a whole bunch of fancy calculations and whatnot, but why not we just balance the thing on a ruler and pick the balance point as the center of gravity? That's probably what I do. So I'll just do it that way, okay? So what I end up with then are the dimensions shown on page 690, okay? So what we've got here is the few things here. We got the total height of the water bottle. We've got the height to the center of gravity where it balanced. We've got a 6 centimeter base. Now, if you look at these bases on these things, they got a little bit of a concave section in the middle is normally how they do these. So the surface resting on the conveyor would be that, kind of a ring around the outside. Now, what I'm doing is I'm modeling that as 2 points of contact at A and B. Now you might say, well, that's not really what's going on there. That's not a perfect model. And I say, yeah, you're right. It's not. I'm just doing the best I can, and we'll get on with it. Okay.
Good enough for who it's for.
Yeah, right. Okay. So what else are we going to do? I mean, we might be able to do a more refined analysis on that, but maybe not. We'll just kind of stick with what we got. Okay. All right. So that's what we're doing here. So let's kind of go through a few little processes with this, and just so we can build the skills to analyze this. And let's kind of get a good systematic way that we can approach this stuff. So let's start by just doing statics, okay? So what I have there listed out for you is that whole inertial moment equation. But with statics, there's no acceleration. So if the water bottle is just sitting there, let's find the reactions at A and B, just to kind of remember how to do that. So in statics, this whole right-hand side just zeroes out. So sum of MA would be 0. Okay, we got the mass of the water bottle, 0.3 kilograms, which is 2.94 newtons. So we need a free body diagram, right? We always need one of them. So what? We'll put that weight at the center of gravity. And then we got the 2 reactions. And that's about it, okay? So there's the free body diagram right there. And then we'll just run through a moment equation. And if you remember with standard moments, normally we call counterclockwise positive, okay? That's the convention when you're doing statics. So what we're going to do then is take that weight times the 3 centimeter, 0.03 meter offset distance. That'll be negative because it's clockwise. Okay. And then we got 0.06 RB that we add to it and set that equal to 0. And we can run through that and solve for RB, and that's 1.47 newtons. So that's the reaction on the right side. And then we go sum of Fy and set that equal to 0. We'll have Ra up, the weight down, and the 1.47 up. Solve for Ra, and that's also 1.47. So the thing's pretty symmetrical, so the 2 reactions are coming out equal. Okay. And that's just a little bit of a statics review. So we got any questions on that? Are we doing all right with that? All right, so we start with that. All right, now let's have a look at what happens if we accelerate this conveyor belt. And let's just make it accelerate at 1.2 meters per second squared. See what's going to happen if we do that, and so this is the second one down there, is things are going to change a little bit, of course. And what's going to happen here is we're going to add one thing to our free body diagram. Now we're going to apply it at the center of gravity because we run everything through the center of gravity, and that'll be 1.2 meters per second squared is what that'll be. And again, that's applied at the center of gravity. That's the convention on this. So that's to the right. So we're going to do the same moment process. We're just going to do it with that acceleration now. Okay. And what we want to do is see what those reactions will be. Okay. So we're going to apply this equation now, and now we do have acceleration. So we don't just set sum of m equal to 0. We're going to set it equal to this stuff here. Okay. So let's see what we got with that. So the left-hand side, and again, I'm getting back to what we were doing earlier in the class, I'll call that the static side. Okay. Just like what we did above, and that's actually why I did that, because I wanted to kind of clarify what the static side is. It's the left side. It's the forces and the weights, the reactions and the weights, forces, that kind of thing. It's minus 2.94 times 0.03 meters plus 0.06 times RB. Now that's going to equal that Ig alpha plus mag xy bar plus mag yx bar. But we're going to come into this assuming the thing isn't tipping, so there's no alpha yet, no angular acceleration, and it's not accelerating up or down, so AGY zeroes out. So I got m, agx, and y bar that I'm going to equate this to, see? So I'm not, let's see, I'm just assuming that the thing isn't tipping yet. Okay, so I'm just going to look at the m, agxy bar side. So that's what I'll call the dynamic side. So what do we got for the mass of that thing? What do we got? 0.3 kilograms. What's AGX? It's right there on the free body diagram, okay? That's what it's accelerating to the right with, so get that filled in. And then look at the moment arm from AGX to point A, where we're taking moments about. See, we're taking moments about point A down there on the bottom. Right there. And our goal here is to find RB is our goal. Let's get the rest of that filled in. So get the acceleration in there and the moment arm. Keep in mind you got an x acceleration, so think about that with the moment arm. So treat it just like a statics kind of thing. Instead of a force, you got an acceleration. Is what's happening here. So what you want to do there is look at the acceleration, which is just right there. And then give it a moment arm. Now that's an x acceleration. So which way is the moment arm going to act? Or which way would the moment arm be to get a moment? Yeah, y. Okay, you mix unlike things to get a moment. So we're doing meters there, so that'd be 0.17 meters. Okay, whenever I think of a moment, what I normally think about is a wrench, okay? So if I've got a wrench on a bolt, like that, if I push on it like that, I use the perpendicular distance, right? I don't use dx, I use dy. If I got an x force, I use a y moment arm, right? So the force and the moment arm are always different, they're 90 degrees apart. Same thing with the acceleration, which I'm using now in the moment arm. So I want the 0.17. That's going to get me a net moment coming around like that. So what's the sign on that? Yeah, it's negative because it's clockwise, just like a statics thing. Clockwise moments are negative. Just look at the direction of acceleration and figure out the direction of the moment based on that. So just like I was harping on before, we want the stuff on the proper side of the equation. So the static stuff on the left, dynamic stuff on the right, and we want the proper sign. Okay, clockwise negative, counterclockwise positive. Okay, we can work through the calculations there. And what are we finding here? The forward reaction on the side it's accelerating towards has become lighter, hasn't it? Because we've got this negative number here. So when we go sum of Fy equals 0, just like we did before, we get a bigger reaction in the back. So what's happened when we did statics, those reactions were balanced, but now they're not. We got a big one in the back and a smaller one in the front. Okay. And if you think about that, you've probably experienced that. If you're in a car and someone really pushes on the accelerator, you rock back into the seat, right? If someone knows about animation and they draw something like that up, I remember the old Roadrunner cartoons. There's always that minute where it kind of just that pause when things start to accelerate, and there's always a little bit of a rock back there. They know about motion when they do animation, right? Then off it goes. You see a lot of examples of this. Okay. Now, what can happen here is if you keep increasing that acceleration higher and higher, eventually you're going to drive this reaction to 0, okay? And that's when you get into something called tipping, okay? And I can show you maybe a couple examples of that where something will actually tip over.
It's not actually considered tipping until RV is 0?
It's actually just less than 0, 0.00000, negative 0.0000001.
So it's got to be off the ground for it to be considered.
Yeah, right. And the forward reaction being 0 is the condition just before that happens. Okay, and that leads to what we call tipping. Okay. And let's see, just some examples of that. Let's see what we can come up with. Okay, here's a simple little movie of an object moving to the right.
Acceleration to the right.
We're just going to move this thing to the right a little bit, and it'll just kind of slide to the right, okay? Without any tipping or anything.
This object has a
Now, let's do the same thing, but let's greatly increase the force, okay? And let's see what happens. So all we're going to do here is do that same thing, but the second time through we're going to have a very large force pushing it across.
This object has a very large acceleration to the right that will cause it to tip.
So very large force, see that thing just tips. It can't keep up. The center of gravity essentially can't keep up with how fast it's trying to accelerate across.
Will cause it to tip.
So it lags, and that makes it tip. That's one way to think about that. All right. Let's see here. All right, so we had a look at the animation, and we had a look at that video. If you're online, it's just motorcycles that are doing some wheelies there. I guess we should tell you not to try that at home, I guess, but it does illustrate that idea that if you just increase the acceleration on a two-wheeled vehicle like that, you can tip or pull up that one wheel. So that tipping is preceded by that front reaction going to zero, okay? And just a little bit more than that, and the front reaction will become negative, and that, in this case, RB would come up off the surface there, off the conveyor belt. So let's figure out what it would take to make this water bottle tip, okay? Now it's the same equation as we did last time. It's just this time you're going to set that front reaction to zero and see what sort of acceleration it takes to cause that is how you would do it. Okay. So here we run the exact same equation. We're considering the threshold of tipping, what it takes to just make that happen. So the moment doesn't have an RB term because we're assuming that goes to zero. So we get 2.94 newtons times 0.03 meters negative clockwise. And then we look at our acceleration in the x direction, which again will be negative, times AGX times its moment arm. And then we can go ahead and solve for AGX. It's 1.73 meters per second squared. Okay. So that's how you could go ahead and find tipping. You just set that front reaction in the direction of acceleration to zero. Okay. Now that's kind of a basic example. We can get into more complex ones, like on page 700 there. Let's look at a motorcycle rider that's applying the brakes while they're going down a hill. We've got a 12-degree incline there, like so. So what we're going to want to do on this is get an axis system set up parallel and normal to that ramp there, or hill, whatever you want to call it, 12 degrees. Okay, so what I did, I just went through and set everything up. So we've got the weight of the rider is 640 newtons. Divide that by gravity to get the mass. Do the same thing with the motorcycle. Okay, and then what we can do here is we can take these weights and break them up into components that are normal and perpendicular to the ramp based on that 12-degree angle. Cosine 12 640 and cosine 12 1400 and sine 12 640 and sine 12 1400. That's the weights of the motorcycle rider and the motorcycle. And we get those all lined out here on their centers of gravity is what we're doing, okay? So I got those weights squared up to the incline there, the 12-degree incline. Okay. And then we can set up an equation here to describe this. Sum of MA is MAGXY bar plus MAGYX bar and I alpha. Now the alpha and the AGY are both zero because the thing isn't tipping yet, so there's no Y acceleration and no alpha. So let's see what we could do with that. Okay, now if we're tipping, now notice how we're accelerating here. Okay, we're going up the ramp because this motorcycle's slowing down. So we're going to go up the ramp like that. So there we go with those accelerations. So if that's the case, if the motorcycle's braking, what are you going to take moments about? Why don't we start with this? Which wheel is going to have a zero reaction on it if you're going to tip? Why don't we start with that? Yeah, it's the back wheel, okay? So this is going to go to 0, because what's going to happen here, if you're going to tip, if you're accelerating up the ramp, it's the wheel on the acceleration side that goes to 0. If you hit the brakes here too hard, you're going to come over like that, right? So that back wheel will go to 0. So if you know that back wheel is going to 0 out, what you want to do is take moments about the front wheel, okay? Because you know that back wheel has a 0 reaction. And what you can do then is set that up, and so the only unknown will be the acceleration. That'll be it, because NB is 0. If you take moments about A, you've got NA acting there, the FNA, whatever you want to call it, and then you've got the friction, but they're both going to have 0 moment arms if you take moment about A. Okay. So that's the purpose for taking a moment about A, is to eliminate these unknowns from the equation. That way you can focus on the acceleration. Okay. So let's go sum of MA is equal to M AGXY bar. So let's go ahead and do that. So what's the sum of moments about A? What are we going to put in there? That's going to be the forces, right? So that normal at B will be 0. So what you're going to do is just basically a statics deal, where you're going to have those 3 forces there, or 4 forces. So you're going to have the 291 newtons. You're going to have the 1369 newtons. You're going to have the 133 newtons. And then you're going to have the 626 newtons. So what you need there are moment arms on these and signs. Now you could do this, have different sign conventions on this. I went ahead and did clockwise positive because the acceleration is going that way. But you could do it either way. It doesn't matter as long as you're consistent. In dynamics, I tend to be a little bit looser on which my sign conventions. I'll often call the acceleration direction positive. That kind of makes more sense to me. But you don't have to do that. It doesn't matter. Okay, and you just got to stay consistent with whatever sign convention you apply. Okay. So why don't you add the moment arms to those and the signs? We're calling clockwise positive. You got to add this to the 0.4. You're doing everything about it. And the 0.76. Get up to 0.33.
Oh, okay.
Yeah.
Oh, okay. So it's like it's got full momentum.
Yeah.
Oh, yeah, that's true. It's not like the center of the bottom of the surface.
Well, we're taking lowest about that point eight.
And point A is that.
Yeah.
Oh, okay, it's not, I was looking at this.
No,
Yeah.
it's not that.
Okay.
Okay, so if we're going clockwise positive, I got 1291 times 0.4. Or excuse me, 291. There's the 291, and there's the 0.4. And then we got the 1369, that's this one. And that's by 0.7. Okay. And then we got the 133. It's this one. And that'll be a combined moment arm of 0.4 and 0.76. So that'll be 1.16 meters. And then we're going to have the 626, 0.7 and 0.3 will get you 1 meter. Okay. So minus plus, minus plus. Okay. All right. And then that's one side of the equation there, okay? Then what we're going to do, we're going to set that equal to m AGXY bar. All right, so we got the two masses. And what are those? Those are 640 and 1400. So those are the masses. Okay, then we got the unknown accelerations.
Aren't this 640 and 1400 aren't those weights?
No, those are, oh, you're right. Yeah, darn it. Thank you. Yeah, those are the given weights. So yeah, I need to get into masses there. So 65.24. And 142.71. Okay. All right, so those are the accelerations and the masses. And then we just need moment arms on those, okay? And signs. So just treat the accelerations kind of like they're force vectors and just find the moment arms to those forces is really all you need to do. Or accelerations, I should say. So there are two accelerations. We just want to find the moment arms to them. And then apply the proper signs. And then you just have one big old equation and you can solve for A. Okay. So that's how I'd be setting that up. So I got the static stuff, just like what you did in statics on the left. I call it clockwise positive, so just get your signs on there the proper way to reflect that. And then on the right-hand side, I got the dynamic stuff, the M, AGX, and Y bar. And I want the proper signs on that too. So I can just set all that up and equate them as I'm doing here. And then I can just solve for the acceleration. So right at 9.89 meters per second squared acceleration, that's when that back tire is about to come up and over. That's how that works. So we got any questions on that approach? That's the way to figure this tipping and reaction stuff out. Just set up that moment equation. I haven't seen, let's see, I just said 29th, right? Yeah, okay. So I'll get you a couple more to be doing for Wednesday. We'll cover these on Friday. So by Wednesday, I mean not this coming Wednesday, but next Wednesday. So we got our midterm Wednesday. I'll get you about an hour and a quarter for that. And then we'll cover a little bit of homework after that on Wednesday. Okay. And then Friday, we'll go over these. There's 5 problems due the next week, so we'll cover those on Friday. Okay, we'll cover some new stuff too. All right, we good to go?